Thank you. Well, I was actually present at the opening of the Westerbork telescope. You can see here Professor Jan Hendrik Oort, who was the main driver behind the construction of telescopes in the Netherlands, radio telescopes. And I'm actually standing here. Okay, so coming to Oort, 40 years before this, Oort was working on the rotation of our galaxy, and he had actually a mass estimate of our galaxy, which Einstein and de Sitter quoted in their paper on the omega matter equals 1 universe. And so that was actually the only mass quote available at the time. And so they thought that, well, the average mass density of the universe as it appeared then, you had one nebula with the mass of our galaxy in a cube with length scale about a couple of hundred kiloparsecs. Oort did then produce a very precise estimate of the mass, not very accurate. Then in this paper, which is well known, he did, after a lot of analysis, he came up in table 34 with the dynamical estimate of the counted estimate of the number of stars, which he found is 0.038 in the solar neighborhood, and from the stellar movement he inferred the dynamical estimate much bigger. And so he thought that it ought to be dark matter, but he thought it was just fainter stars. Nowadays, we think that most of that dark matter in the solar neighborhood has been found in the form of gas of some sort. And actually Oort found some hit by promoting radio astronomy, and the H1 values are based on a survey done with this telescope, which is a Dwingelow telescope. There is still a question of a dark disk, and that will be discussed in the big conference this week by Justin Reed. It is expected in Lambda CDM that there should be a light dark disk, and we have to wait for Gaia to actually settle that question. So the question is still open. Zwicky, pictured here, came in a 33 paper, which is not well known, not well read actually, because it is in German. And he did that actually, he took the 8 known velocities from Emerson and Hubble, noticed that the dispersion was 1,000, and he calculated that the dispersion should be 80 kilometers per second, based on the assumption that you have 800 nebula, each weighing 10 to the 9 solar masses. He came back to that in a 1937A, a physical review note. He said that, well, I showed the mass of the nebula is 4 times 10 to the 11, and Hubble tells me it is 10 to the 9, and so there is a discrepancy, and that can be settled by gravitational lenses. So he thought that, well, most of the missing mass he identified would actually be in the galaxies. Progress was very slow at the time, because in 1954 there were only 22 velocities for the Coma cluster, compared to 8 in 1931. This is the distribution of the 8 galaxies, because you can trace back which galaxy was measured. And this is the Rosat X-ray map, already discussed in the previous talks about the baryonic catastrophe paper by Simon White et al. In 1993. And there is actually more mass in the gas than there is in mass in the galaxies. But there is still more dark mass. And so the lensing is now also used as a measure for galaxy masses and cluster masses. On to rotation curves. Most of the talk will be on rotation curves. So I note that Curtis in a review article suggests that Newton's law may not hold for distant objects. Zwicky predicted in this FJ paper actually a rotation curve shape like this. And Babcock observed the rotation curve of M31. He did it at a 36-inch telescope at Lick. The inner part based on absorption lines, the outer part based on emission lines in the blue. And so he had measured only 4 points. Because usually people presented with the reflected, so these points reflected the other side. It fills the diagram unnecessarily. So he noticed that, well, there is a discrepancy between what you expect for the outer rotation in the outer parts of our galaxy, which are the so-called planetary type, and what I find, which is constant angular velocity. Now, some people call this constant circular velocity, but that's, of course, not the case. Also note that the exposure time for that point was 3 nights, and the data have not been confirmed with modern measures. In the 1950s, it was possible to develop 21H1 line work based on the prediction by van der Hulst that there should be a line at 21 centimeter. And the first rotation curve of our galaxy was published by Quay, Mulder, and Westerhout, based using the code-wave antenna. And then when the Dungelong antenna came into play in 1956, van der Hulst, Raymond, and Verwoerden measured M31. And these are the actual measurements. So this is a velocity scale horizontal and spatial scale. And you can see the change over. So, and they determined the model, because you have to model the velocities, because you get this smearing partly because of the beam size. The beam size is rather large compared to the extent of the galaxy. And so actually this point is just one independent point in terms of resolution. In the meantime, Schwarzschild had analyzed data from Mail, which was Babcock's supervisor actually, and he argues that mass follows light in M31. So he made so-called normal points from a scatter diagram. You can make normal points by just taking judicious means, and then he could fit this with a curve based on the light distribution. In the late 50s, Kahn and Walter looked at the M31 Milky Way problem, noticed that the speed was the speed of approach, that is away from the Hubble flow. And so they calculated that the mass of the local group should be bigger than 2 times 10 to the 12th solar masses, which is much bigger than the masses of the individual galaxies. And so they thought it was intergalactic gas. And they even thought that the H1 warp, which was known to exist at the time, could be explained by the drift of the Milky Way in that gas. But this was forgotten. And it wasn't even connected up with the rotation curve previously discussed. This is a bit strange, actually. Then for binary galaxies, most of the work was done by Thornton Page in a long series of papers. And he noticed in a review paper, which you can find on the web now, that you have the log of the mass-to-light ratio as function of the number of the galaxies in a group. And so here you have coma. So he found back strictly the result, of course, or maybe used it even. And then the outlying points here are based on individual rotation curves by Burbidge, and Prendergast. And then there is a point here on double galaxies based by Page himself. But in the 60s, a lot of people were drawn to other objects like quasars, pulsars, and also the microwave background. Sorry. Okay, then I will come back to the sequence later, but I noticed that some people are a bit confused about what is to be actually expected, and some of the confusion has been shown by Vera Rubin, who in popular talk says, oh, well, you observe a rotation curve which is flat, and you expect a rotation curve that rises and drops rather quickly beyond outside the the nucleus. It decreases in a Keplerian fashion. Well, that's probably not expected. We saw this in Gianfranco's talk already. But in 1978, she published a paper where she fits a disk model, and that fits rather well. Or a disk plus bulge model, which also fits rather well. So what's going on? Well, a similar argument was done by Ostraker and Mitten in a book, in a figure. When I saw the figures, I thought, oh, well, I know this figure. Because this figure is actually from Wikipedia. Now, from Wikipedia, you can trust Wikipedia, but you should verify whether you can trust it. So there is a footnote which says that, well, this is from work in 1991. Okay, fine. But that's modern work. That's not old work. And Ostraker asserts that these are the points of Burbage, and Prendergast, schematically. Well, it's okay, it's schematically, yeah. So anyway, and they also claim that Rubin's curve follow B. Well, let's see whether that's true. When I did my studies, I looked at Freeman's paper, and his main paper contains a description of the light distribution of galaxies, defining a spheroidal component and an exponential component. This is just log intensity as function of radius, linear radius. And so you find this exponential component, and when you go back, the central surface brightness seems to be constant for many galaxies with a relatively small scatter. This is the formula in surface brightness. So you can work out that the rotation curve at peaks at 2.2 scale lengths, and that the optical radius of a galaxy is typically at 3.2 scale lengths, which is here, and so it's just flat. So you get the flatness just because you don't go very far out. And what matters is the radius of the last measure point compared to the optical radius. So you can, for every rotation curve data, I then just simply worked out the radius of the last measure point compared to the optical radius. And I find for the sample of Burbage, and Prendergast that they are clustered here. But I first looked at the Wikipedia thing again and tried to figure out what the hell it was. And it is actually an exponential disk, almost, except in the outer parts where it peters out completely Keplerian. But it goes out to 20 scale lengths. Well, there aren't many rotation curves going out to 20 scale lengths. So actually, Burbage, and Prendergast, they go out to 2.44 of the optical radius only. Rubin's data in 1980 goes out to 0.83 of the optical radius. My early data from the 1970s go out further, are the red points. And the Begeman et al., which was inspiring the Wikipedia artist, go out a bit further by design. And so the presence of dark matter can be derived from a flat rotation curve, but only if it is of sufficient extent, that is 5 disk scale lengths or more. And so 21 centimeter line data going much further out are a better probe. And then I still don't know why the schematic is so different from the reality. So I'll ask them at some point. Okay, now you will not be surprised that if you take the rotation points of Rubin and Ford in 1970, even though it's very great advance, and certainly much different from the Babcock effort, you can still fit it with an exponential disk based on the scale lengths given in Freeman 1970. And so the dark matter in M31 is established only with radio data. And Freeman's appendix is often quoted in the dark matter context more often than his main paper. He says that, well, for a couple of galaxies, I looked at it, and the photometric outer edges, the data just reached a turnover point, which means that there should be dark matter. Okay, if this is correct. Well, it took some time to establish that it was correct. Well, okay. So for M31, there was actually a debate between Maud Roberts and Joel Baldwin in an IU colloquium in '74 on the validity of just the H1 data. So Baldwin et al., Emerson Baldwin, found that it goes like this, it goes like an exponential disk. They didn't specify with scale lengths, but okay. Roberts maintained, yes, it is flat. And so they were arguing which data is valid. Because part of the problem was that Roberts' data was single dish data, and single dish data are known to have single dishes are known to have side lobes, and you can pick up with the side lobe, you can pick up spurious signals through to the error beam. And so you can think that if you measure here, you can get a point, but it is just through the side lobes. And you measure actually at this point, you measure emission from this area. And that is what's shown here. This is with a beam with a 140-foot beam of 21 arc minutes. So these points are dubious. These are just from emissions from here, picked up through the error beam. And the extent, this picture is a Westerbork picture of a mosaic at very much higher resolution. You can see that the extent of the emission stops at 150 arc minutes. So any point beyond this is spurious. Roberts actually went to Bonn, to the Effelsberg telescope, which has a better behaved beam pattern, and reconfirmed his own data. And in the end also, the Cambridge people came up with better data, also confirming the. Okay, now to the Ostraker and Peebles study. That was a completely different study. Namely, people were starting to play with computers at the time, and there was sufficient computing power to actually start seeing what happens to when you load up a mass distribution in a disk and you just let it run as an n-body system. And so this, for example, Hall did this. The evolution of a disk of stars with initially exponential mass distribution. And so the first snapshot is this, and sometime later it evolves, and then it forms a bar. And then the bar it just becomes stays there and is robust. So, in this paper, with this intriguing title, "Can Cold Disk Stellar Galaxies Survive?" Supported in part by the National Science Foundation, they came up with a trick which doesn't cost much money at the National Science Foundation, which is that you just fix it up with a halo, a spherical halo. If you add it as a fixed potential, makes the model more stable. Then they came with a reasoning. This implies that since the halo mass has to act on the disk mass, the halo mass interior to the disk should be about equal to the disk mass. And therefore, exterior to the disk, the mass could be extremely large. All this was based on simulations with 300 to 500 mass points only. And it was difficult to convince observational astronomers. They couldn't see anything. Because after all, the convincing act for Neptune was Leverrier telling Galle where to look for and what to look for. And so this was just an hypothesis. But it was followed up by a set of papers in 1974, Ostraker, Peebles, and Hill. Also, Enasto, Kartik, and Saar in Estonia. And they noticed that, well, from a variety of indicators, if you make a plot of the mass as function of radius, it just starts to increase. There are some odd points. There's this odd point by Page. It doesn't agree entirely, but the trend agrees between Einasto and Osterreicher et al. And a lot hinges on binaries and groups and so on and so forth. That was studied. More binaries, galaxy samples were made by Turner, by Peterson, and were discussed also by Simon White, who became an expert on analyzing those things, and found that the problem is rather tricky. You need accurate redshifts, you need to vary with true memberships, orbits, etc., etc. And so the acceptance of this idea of this big dark halos was not instantaneously at all. There were even some people who wrote against it, Burbidge in particular. He gave some arguments. Well, the increase in M31 is only 40% in mass. And Astro rejects non-circular motion without even giving the reason. The mass estimates are large radii are uncertain, and et cetera, et cetera. You can see that here for this group, for example, yes. This is a group of 5 galaxies called Stefan's Quintet. This galaxy has a redshift that's completely off with respect to the others and thought to be foreground. That was also controversial by itself. But the other two, these two, they are interacting. But the velocity difference is 850 kilometers per second, which is quite a lot. Quite a lot more. Okay, on to rotation curves. Some of these arguments were based on rotation curves of Roberts and Rods on the one hand, and Rockstead and Shostak on the other hand. Now, this is M81, which they took the south part because M81 is interacting, and they took the rotation curve of this part. The rotation curve of the other part goes up. So it's a bit strange. M101 is interacting. The symmetric part is very small compared to the total size of the galaxy. So you never even should do a rotation curve of that. For our galaxy, we don't know. And so the argument really hinges on M31, as I showed before. And then Shostak, Rockstead and Shostak, their data is they use a thing called R80, the radius within 80%, which contains the 80% of the H1, and it is only goes out to the Holmberg radius, which is 4.4 scale lengths, so it doesn't go out very far either. Then the Anasto paper is rather more complicated because the tables weren't published with the paper itself. And so you can only find it back now on his website in a preprint form. I pick out one galaxy with M33. You can fit the data for M33 out to the last Massey point at the optical disk without dark matter. If you add the points, you have to add the warp model, the galaxy's warps. And these are deeper H1 pictures with the VLA. You can see how strangely the H1 behaves. In any case, it was mapped again by Corbelli and Salucci using Arecibo. And they found this rotation curve with somebody canonized and iconized in this curve. And sometimes people show Vera Rubin's picture rather than the original authors. So, but in the PANDAS survey, McConaughey and all show that, well, there could be an interaction, and so with M31, and so it's not entirely sure whether you can assume circular motion in the rings. From my own work, I did some dull galaxies without any spiral structure, like this one. This is the Burbidge and Prendergast effort. And this is a modern effort on the H alpha data. And these are on the same scale. And my velocity field is this much bigger. And so I go much further out. And if you know how to interpret these diagrams, these velocity diagrams, you can see that the rotation curve stays flat. And I show that actually this is the galaxy here, one of these. And so I collected up in my thesis all these galaxies and presented it in various places. I did my own observation with the Westerbork telescope here. This is another galaxy. And this is the optical image as I had it. And I showed that to the Vauquelin. Well, this is the optical image. Guess what is the size of the radio image? And he said, well, I should just will fill it here, right? And then I showed him the plot, which was 1 meter long. And so he ran out of my room, saying, I don't understand anything about galaxies anymore. So, okay, and so we also, with Van der Kruit, we went to collect photometry. And you find the local ratio of mass to light actually increases to very large values. And we established that for quite a number of galaxies. And also for the M31 model, it's quite well established. So now coming back to Vera Rubin's work, well, the last point matters, as I said before. And Carl Noyes in his interventions made that clear, that you need to evaluate the contribution of the baryons before deciding whether dark matter is required. So you need to do the photometry. Now, it turns out that Rubin's data sample was only, the photometry was only done in 1986 or 88 by Steve Kent. And he found that, well, if you decompose it, here if you have the light distribution, you can predict the rotation curves which actually fit the data of Rubin's. Basically because the data don't go far enough out. Even though the spectra look very convincingly flat, that's fine, but it simply doesn't go far enough out. Even for this galaxy, which is the biggest he had, the discrepancy starts here. In the very last point, optical, but it's confirmed by the H1. And so this point has been made frequently. Okay, the dark matter was also found in dwarf toroidal companions. Based on 3 stars, Aronson decided that there should be dark matter. Now we know that this is confirmed, with many more stars. And these dwarf toroidals, yes, they play a role in constraining lambda CDM. And so now people have been surveying out around the Andromeda. They have 26 dwarfs around our galaxy and so on and so forth. Briefly, now it is established, based on rotation curves, that there is dark matter, but we don't know how much. It's still under debate how much. And various dynamical arguments can be put forward. Here we have the paper in which we use spiral structure theory, and we find a range of values for the mass-to-light ratio. You can see, but based on other data of velocity dispersions, the tendency is to be lower, sub-maximum disk. So that is still under debate. The shape of the dark halo was initially thought to be round, but this method is much more scattered now. This method was, people hoped that with flaring H1 disk one could do something, that it doesn't turn out to be the case. Nowadays, we have multi-wavelength observations of these galaxies with surveys like things, and so on and so forth. The term flat rotation curve is maybe appropriate for bright galaxies, but certainly not for faint galaxies. Okay, it flattens off, but that's all. And in this particular dwarf galaxy, the decomposition shows that the dark matter curve, the dark matter component, is almost equal to the total component. So you can use that as an indicator. And so we did a number of those galaxies and tested lambda CDM quote-unquote predictions at galaxy scales. Now this problem is around for some time now. And you can see it here that the N of W simulations seem to predict rotation curve shapes like this, and the observed points are much more linearly rising. Which means that the dark matter density coarse rather than stay cuspy. And this is the latest work, and it still is clear that the N of W is off. Finally, this stability, was it a problem or not? People forget sometimes, yes, sure. People forget sometimes that this stability was invoked. The Ostreicher people's paper did produce an impact. This was studied by Atanasula and Selwood, who found that, well, okay, bare disks, if you have little random motion, the bar falls quickly. If you put in a lot of random motion, it can stabilize. If you decrease the active fraction, you can get stable models. The other thing Atanasula found was that, Jim just introduced a fixed potential in his 10-body model, but that is not enough. If you put a live halo, you get a big bar. And that is because a live halo can absorb angular momentum via resonances, so a strong bar develops. This has to be modified if you introduce gas, because then the bar becomes less strong, or a mildly triaxial halo. But even so, so the stability argument paper of Ostrek and Peebles is formally wrong, but it was a very productive paper. Why is this important? Because the bar in our galaxy influences the inner mass distribution. And so for dark matter detection experiments, it is necessary to actually know what the mass distribution of our galaxy is. Now, when a bar buckles, a structure forms like a box peanut. And actually, orbits are unstable, and they go out of the plane. And by symmetry, they become X-shaped. And this X-shape has been detected in our galaxy as well. This is the bar of our galaxy, and you can see the X-shape if you know how to look for it. And so it could be that the bolts of our galaxy is actually just formed from the disk by this mechanism. Now, we know for another galaxy which has been lensing, we know that it is barred, and we know that the bulge is maximum. And so from the lensing argument, which means that for our galaxy, we should also think that, well, it's the baryon which dominates the center, and not the dark matter. So I think I stop here. Thank you.